So I'm Robin Tichy from Micropower Electronics. The topic that I'm going to discuss today is portable power for medical device design. Specifically, I'm going to be talking about battery packs, though. The agenda for the talk is going to be just a little bit about micropower and what we do, and then the basic migration to lithium ion away from other types of battery chemistries. And then I'm going to talk about a few short topics that are particularly pertinent to medical device design. So fuel gauging accuracy, unique form factors, including lithium polymer, high rate batteries, and sealed lead acid replacement, basically talking about the new lithium iron phosphate chemistry, and then sterilization of batteries that use lithium ion chemistry. So rather than talk very generally about portable medical device design, I'm going to touch on a few specific topics that I think are really relevant to medical device design today and can help you get ahead of what's going to be out there in the future and what the competition is going to be doing. Can you guys all hear me okay? There's a lot of noise over there. Okay, good. So Micropower Electronics has been in business designing portable power for mission-critical applications. In other words, we only do custom battery packs and chargers for medical, military, and industrial equipment. We've been in business for about 25 years now, located in Portland, Oregon, where we have design and manufacturing. We also have a group up in Seattle, where I'm located. And then we have Asian manufacturing for some of our higher volume applications. We are both ISO 13485 certified and FDA registered as well. So if you're familiar with battery pack design or what the different components of a battery pack are, if you've only worked with, say, nickel metal hydride or sealed lead acid batteries, you may not recognize all of these different components. So today, a battery pack is much more than the individual cells, which are the fundamental building blocks of a battery pack. It also includes battery management electronics that provides necessary safety, charging control algorithms, and also gas gauging and information transfer to the host device. There's also generally a plastic housing, which can be quite complicated if you're, say, designing a sterile application. Of course, there's enclosures and the removal latch and all that sort of thing as well. So this is a graph showing the volumetric energy density and the gravimetric energy density of various general battery chemistries. So if you're familiar with lead acid batteries, the energy density of that type of chemistry has really been pretty darn low. Lead acid batteries, though, do have their place in some types of backup applications for various reasons that I'll get into a little bit more later. NiCad and nickel metal hydride, of course, maybe a 2 or 3 times improvement, whereas lithium ion is maybe a 10 times improvement over older sealed lead acid technology. Now, I think one thing that's kind of interesting to point out about this graph is that this lithium ion bubble is quite a bit larger than these other bubbles, and what that signifies is that lithium ion is a catch-all description of quite a few different chemistries with quite a few different properties. So what I'd like to touch on today are a few of those different variations of lithium ion and how they can be used in medical applications. So because of that extreme increase in energy density for lithium ion versus the other chemistries, what we see here are the various battery chemistries like alkaline that you may be familiar with, lithium, that's lithium primary or non-rechargeable lithium, lead acid, lithium ion based chemistry, nickel, and others. And what you can see here is that we actually do see still a pretty extreme growth of lead acid for various reasons, most of them grid applications or automotive applications. We also see a much more extreme growth of the lithium ion rechargeable applications in the coming years. So getting into these specific topics for medical electronics, first one is gas gauging. Now, one of the advantages of lithium-ion chemistries over the others, besides its energy density, is that it has a very flat discharge curve. In other words, the voltage stays very flat regardless of what kind of current you're drawing out of that chemistry. But most gas gauging algorithms in the past have been, say, a voltage monitor for sealed lead acid, because if you look at the voltage discharge curve of the lead acid, it just goes down very quickly, and you can very easily monitor what the voltage is and then what the remaining capacity is. You can't do that with lithium ion. There are other, the nickel chemistries usually use what's called a Coulomb counting algorithm, where basically you look at the number of electrons going in and out of the battery, and then make an educated guess about what the remaining runtime will be or what the remaining capacity is. The problem with that is it goes out of calibration really quickly. With lithium ion, there are more advanced algorithms to use, where you use a combination of Coulomb counting and a voltage monitor and a complex algorithm to get a very good description of runtime to empty, and you can get a countdown with like 99% accuracy of how much juice you've got left in your battery. And that's really important for medical applications. This picture I've saved for about 5 years now because I think it's just totally awesome. This was actually taken by a doctor that I was working with, who I put in a request to him, can you go around your hospital and take pictures of places where you see problems with batteries in the hospital? And this was my favorite one. They had this whole room full of these infusion pumps, and the system that the hospital was using to show whether or not they were charged or not was that they would put a pink charged ticket on the good ones and a green uncharged ticket on the ones that hadn't been fully charged back up again yet. And this is not, in my mind as a patient, that's not exactly the way I want my medical equipment to be maintained. I'd much rather have a really accurate gas gauge. So these new lithium-ion gas gauges that are available can be a real advantage for those of you designing medical equipment. So essentially the new gas gauging algorithms, they combine the advantages of voltage and current-based methods. They use a voltage-based method when there's no load. In other words, they monitor the open circuit voltage opportunistically when there's no load to determine the state of charge. And then they use a current integration or a Coulomb counting based algorithm when there is a load. So the problem with the voltage-based measurement is if there's a load, you don't have open circuit voltage, so you can't look at that. And then they update the impedance. So the impedance of a battery changes over its lifetime, so you need to look at that as well, using both the voltage and the current information. And then they use that to calculate remaining runtime with a given average load. Now that's very important, especially if you're designing, say, a life support device. All right, now I'm going to go through lithium polymer, and I realize I'm going through these topics really quickly, but I just want to give you an idea of what's available, and then you're welcome to ask questions afterwards or come by our booth, send me an email, whatever. So lithium polymer. The advantages of lithium polymer. So lithium polymer versus a conventional lithium-ion cell. Lithium-ion cells generally are spirally wound anode and cathode material that are then inserted into a metal can that's either a brick shape or a cylindrical shape. Lithium polymer batteries, on the other hand, are manufactured in layers and then stamped into individual sizes. So you can get all different sizes and shapes. And the advantage is that you can have very low profile, a flexible form factor. In other words, you can stamp that shape out into basically any shape you want. They're extremely lightweight because they don't have a metal housing around the cell. And you can get them very, very thin, and actually also very thick and very large size. Limitations: packaging's fragile. You need specialized tools. They tend to be more susceptible to swelling, which is one of the problems in batteries in general, is that the cells will swell over their lifetime. It's totally normal behavior, but it's something that you need to be aware of when you're designing. And there's also a price premium. So lithium polymers are also projected to grow over the next decade. So, like I said, because lithium polymers are actually made in a laminate form, sometimes they're called laminates instead of polymers. You can see that they are projected to grow significantly from a very small market share to pretty significant over the next couple of years. So what can you do with lithium polymer? Well, the big thing is that you can make something thin. So some of the recognizable applications for lithium polymer, Motorola was the first to make use of this technology, really differentiating their products with this with the Razr phone. They're don't seem so special anymore, but at the time that was really exciting to have a phone that was so thin. Of course, now Apple is making really good use of this polymer thin form factor and showing off just how incredible that looks to have such a thin notebook computer. But we are seeing introduction of lithium polymer into the medical space as well. So this is a battery pack and charger that Micropower designed for Carestream Health, which used to be Kodak. And this is a battery pack, and this is the charger that it fits in. The battery pack is very thin. If you want to, you can come by our booth and see it. And it's actually designed to fit in, to make a digital X-ray plate out of a normal film X-ray cassette. And so the battery actually has to fit in what used to be a film X-ray cassette. So it's very, very thin, and has really been a great advantage for this company to be able to design something like that. All right. Next topic, quick topic. Iron phosphate, high rate, and SLA replacement. So, as most of you are in the medical industry, you're probably aware that lead acid is used quite a bit for backup power applications. So there are a lot of applications that use this lead acid for backup applications, like these medical carts, oxygen concentrators, infusion pumps, ventilators, all those types of class 3 medical devices used for life support. They all need backup power. But a lot of them are becoming increasingly mobile. So you see something like that infusion pump that I showed a few minutes ago. That's actually wheeled all over the hospital, and people are almost using them in a mobile type way. So because lead acid is so heavy, it'd be really great if you could use lithium ion instead. The problem is that lithium ion has had some challenges when it comes to using it in a backup application. So lithium ion doesn't accept float charging, historically has not accepted float charging very well. It also has a cycle life of, say, 300 to 500 cycles, which is not really enough to last the lifetime of a product. But now there's been an introduction of iron phosphate chemistry that happens to have a voltage of 3.3 volts or 3.2 volts operating, which means that if you wire several cells in series, you can get 12 or 24 volts, which matches really well to a lead acid battery. It also can accommodate float charging. This is partly because it's been designed for high rate. It tolerates high rate, which has the advantage of also tolerating a lot of fluctuation in the charge current, which typical lead acid batteries have a lot of fluctuation in their charge current. So that's been a challenge for lithium ion. But now with iron phosphate chemistry, you can adapt to that. The way that this is done is by using iron phosphate chemistry and also just designing the cell so that it's for higher rates. So you use thin materials, thin current collectors, and a much higher electrolyte concentration. So this is an example of the types of rates that this iron phosphate chemistry can tolerate. So this is a 26650 cell. Battery cells in general are designated by this first number is the diameter of the cylinder. The second number shows the length. So this is 26 millimeter diameter, 65 millimeter long cell. And a single cell can put out, delivering its full capacity, so full capacity of say 2.2 or 2.3 amp hours at up to 30 amps. So that's a huge, huge current. It's great for lead acid backup. It's also great for things like surgical applications where you have a motor that has a high current draw. Another advantage of lithium iron phosphate chemistry is that it's safe, which is another thing that you're interested in if you're replacing lead acid in a hospital application. This graph right here shows weight loss versus temperature. So you raise the temperature and you look at what the different chemistries are going to do. Are they going to lose weight? In other words, how thermally volatile are they? And what we can see here is this iron phosphate chemistry loses very little weight even at very, very elevated temperatures, while the other battery chemistries are all losing some of their weight, which means it's a lot less volatile and a lot less prone to what in the battery world is known as thermal runaway, or various euphemisms that mean explosion. So micropower is actually designed a direct replacement for lead acid batteries. If you want to come by our booth, you can see this. It's a standard replacement for a U1. It's a 12 volt, 40 amp hour lithium iron phosphate battery. Versus lead acid, it gets longer cycle life, so we expect 2,000 to 3,000 cycles out of this battery, whereas lead acid would be maybe 200 or 300, so about 10 times the cycle life. It's lighter weight, maybe about half, so a lead acid battery this size would be about 25 pounds. This one's about 13. Longer run time, faster charge time, so you can get full charge on this battery in about 2 hours. Longer shelf life, and overall lower total cost of ownership versus a similar sealed lead acid. All right, last topic, sterilization. So what we've seen at Micropower designing medical batteries over the last 25 years is the first adoption that we saw was what I'll call the patient's room. So we saw things like patient monitors and ventilators start to adopt battery technology and become increasingly portable. We also have seen a lot of battery adoption or portable power adoption in the emergency field. So using defibrillators out in the field, using the heart thumpers, things like that. And now what we're finally seeing is an adoption of more advanced battery technology in the surgical field as well. So surgical instruments have kind of a unique need. They need the battery to be untethered, or they need the device in general to be untethered. And that's because any cord could be viewed as a breach of the sterile zone in the surgical suite. So there's a definite need for having a battery power rather than a cord. They also need high power, so those high power cells are very important to surgical applications because you have, say, a motor for an orthopedic tool for a bone saw or something like that, so you need really high power. Generally larger multi-cell packs, and then you have this sterilization need, and that's a real challenge for batteries. For sterilization in general, if you're in this field, I'm sure you know, there's several options. Autoclave, Sterad or Steris or hydrogen peroxide sterilization. Then there's aseptic transfer is one possibility. And if you're doing non-rechargeable batteries or surgical equipment, you might use gamma sterilization or ETO. Each one of these carries its own set of challenges for a battery pack. So historically, surgical applications have used batteries like NiCad because they can tolerate the high temperature of autoclave, or use alkaline with gamma sterilization because it's not damaged by the gamma sterilization. But now what we're seeing is that with the adoption of, say, hydrogen peroxide or aseptic transfer becoming more common in Europe, lithium ion is also becoming very common in surgical applications. We are also seeing an adoption of lithium primary because of its higher rate capability and higher voltages in applications that are using gamma or ETO sterilization. So just a little bit of market information. What you can see here is, say, the last 2 years, there's been just a small adoption of lithium-ion technology for both the orthopedic and the general surgery markets. But what you can see here is that, according to Frost and Sullivan at least, by 2013, the battery market for surgical applications is going to be about $75 million. So that's a huge growth from, obviously, from 2. This is actually a battery pack that Micropower is manufacturing right now for this orthopedic tool. One of the challenges here is that the usage model hasn't yet been determined. So because this is not a really common type of application, we don't have a really good feel yet for how the doctors and nurses are going to use their batteries in a sterile environment. So it's hard to determine. It's basically up to all of us who are designing medical equipment to determine what that usage model is going to be, and then design accordingly. So there are a number of different options. For example, and they all have different effects on the battery. So these would have the most heat and corrosion for the battery, least heat and corrosion for the battery as we go through this cycle. And there are these options along the way about what's going to happen in the hospital. And it's yet to be determined what process flow the battery is going to see. So it'll be used, and then in some hospitals, the battery would go through an automatic wash cycle, which is very high temperature, very corrosive detergents. In some cases, it'll be removed from an aseptic transfer pouch. In some cases, it's just wiped down. Then the battery is charged. It could be autoclaved. It could be fast autoclaved. It could go through hydrogen peroxide sterilization. And then it'll be stored for use. And in some cases, it'll go back through an aseptic transfer process. And so autoclave is obviously very high temperature. Sterid and Steris has this hydrogen peroxide gas, which will be corrosive for electronics. So in each of these cases, no matter what you choose, there's going to be various challenges. And because nobody's really determined exactly what is going to be the standard for batteries, you almost need to design for all of them. All right, so that's all I had. I know I breezed through a whole bunch of different topics, but I was hoping to leave just a couple minutes for questions. Or feel free to contact me afterwards and pull me aside and say, you breezed through that. What were you going to, how is it relevant to my application? Are there any questions? We've got one up here in the front.
Swell?
Yeah.
How much do they swell? Is it the inside of the package that's swelling, or is the whole package swelling? Or
Sure.
Is it like a volume by how much they swell, or what percentage is it?
That's an excellent question. So that's something I breezed through, that there are a lot of details like this that need to be worked out in a battery pack design, and I can't really go through everything in 20 minutes. But as the battery is used and cycled, the working ion or the lithium ion cycles in and out of the material and actually causes the material to swell a little bit. It's totally normal behavior. If you're looking at a lithium ion in a cylindrical package, there's actually no swelling because the hoop stress around a cylindrical cell is so strong that the cell won't swell. But if you have a prismatic, which is a sort of brick-shaped battery or a lithium polymer, you can expect that outside the long edge to bow out over time. And you should accommodate for basically 10% swelling. And because of that, it's generally not advisable to stack more than 3 or 4 cells on top of each other, because you can have that added, and sometimes it'll do something like even crack the external case of the battery. Any other questions?
Nickel metal hydride, you have to do recalibration if you're doing Coulomb counting. After so many cycles, because the cells degrade. Do you have to do the same thing with lithium ion? And also, do you have to do cell balancing with lithium ion?
Depending on the gas gauge you choose, but generally speaking, you don't need to. The gas gauging in lithium ion does not need to have calibration. It periodically will self-calibrate, so that's one of the advantages. Cell balancing is advisable in many situations, but generally speaking, it's not required unless you have more than 4 cells in series. So unless you get to very large packs with very high series cell counts, it's not required, but it does help. So if you really need a really long cycle life, then cell balancing would be something you'd want to do. Are there any other questions? All right, thanks everybody, thanks for coming.